hopefully everybody can see my screen okay. So good morning, everybody. Like David says, my name is Paul Firth. Over 33 years now. In September, I just hit another year, so 33 years in the cement industry. My current role is an emission monitoring technician. And as David has already said, I'm the process operator officer at the Source Testing Association since 2018. Following from Rod's and David's presentation, without question, lower best available technique associated emission levels, and in turn ELVs has a direct impact on compliant particulate calibrations. The presentation I'm going to give today is really on the uncertainty and variability on compliant calibrations at low particulate emission levels. So I'm going to focus on particulate emission levels and pick out some extracts of the standards, but also cover the emission monitors as well. Apologies in advance. I will try and talk over these, but there are a number of acronyms through the presentation. So I've given a guide here, but I will be talking over these. So hopefully the acronyms won't impact anyone through this presentation. So apologies in advance if they do, but I have given a guide here of some of the acronyms used in the presentation.
Sorry, Paul, is it possible you can put it into full presenter mode because we're seeing your next slide?
Right, well. Okay, sorry. Let me,
I think it's in display settings at the top.
Right, okay.
Yes, swap presenter view and slideshow.
Is that better?
That's great. That's perfect. Thanks, Paul.
Yeah, apologies for that. The presentation is broken down into two parts. The first part is going to cover low particulate levels and some of the technical issues and extracts from the standard reference methods, BSEN 13284 Part 1, 14181 and 13284 Part 2. And also I will cover low particulate levels and influence on continuous emission monitors, also known as automated measuring systems. At the end of the presentation, I'll also cover a section on control chart approach, which offers a viable alternative when particulate monitors cannot be calibrated. Before we begin, one point to consider, and this really affects all continuous emission monitors on the market for particulate or certified continuous emission monitors on the market. So this is an extract from a MCERT approved continuous emission monitor, and I'll just read it out. To measure the dust concentration, the correlation between the primary measured variable scattered light intensity and the actual dust concentration in the duct must be established. For this purpose, the dust concentration must be determined by means of gravimetric measurement. Just to make the point clear, no dust monitor on the market today that's MCERT certified will give you a dust concentration the minute you put it in the stack. Most manufacturers will ask you what's typical concentration, and it will output the concentration or the output from the response from the continuous emission monitor will be set where it's believed the dust concentration is. But ultimately, to be able to report these emissions and to calibrate, it must be calibrated against a series of standard reference method tests. So again, just to make it clear, this statement is taken from one operating manual from an MCERT approved continuous emission monitor, but holds true for all of the MCERT approved particulate analyzers currently on the market, regardless of manufacturer or measurement principle. I just want to make that point clear at the start of the presentation. So really, just to break things down in simple terms, the basic particulate standard reference method 13284 Part 1 forms the principle of wear dried filter paper, draw a known volume of air through it, dry and weigh the filter paper again, and divide the difference in mass by the volume. Of course, this is the in-stack test. For the outer stack, there's also the include the rinse solution, but this is just an overview of the basic standard reference method for particulate matter, total particulate matter. And just to give a bit of an overview on the standard, when the 13284 Part 1 standard was first developed back in 2001, like a lot of standards, like Rod has covered already, validation work was completed on this standard at two plants. They were both municipal waste incinerators. Plant A was a semi-dry process with a fabric filter and a stack gas temperature around 140 degrees. So as part of this validation work, 4 teams tested the same stack at the same time, and the results varied between 3 to 19 milligrams from 32 tests. Plant B, again, municipal waste incinerator, but it had an electrostatic precipitator with a scrubber, a wet scrubber, and the stack temperature was about 60 degrees. And the 3 teams using the standard return results of 0.3 to 6.8 milligrams from 16 tests. I think these variation in results, which are at the back in Annex D of the 3284 Part 1 standard, the original standard in 2001, I think it's important to recognise in the context of new best available technique associated emission levels of 10 milligrams of less for particulate matter. Now, as it stands, and we've heard talk about validation work, the 13284 Part 1 standard was revised in 2017, but the validation work wasn't recompleted. It wasn't done again. So this is the only validation work we have for the total particulate matter, low particulate matter. Without question, these tests were typically 30 minutes, and if the test time was increased, it's recognised that the uncertainty and the variability would reduce. But I think it's important, especially when such low BAT AELs, best available technique, associated emission levels are being set, that really this revalidation work needs to be revisited. We need to understand where the uncertainty is at this point in time and moving forwards. So the Environment Agency Technical Guidance Note M20, section 3.5.1, verification and spread of data. They do provide a graph, and I think David showed another similar example. Really, this is an ideal calibration with low, medium, and high data points. In reality, you wouldn't really get this sort of level of spread and agreement on particulate matter. In essence, look at these scales on the X and Y. This type of calibration is no longer possible with the onset of best available technique associated emission levels of 10 milligrams or less. Ultimately, in simple terms, you need a good spread of data in order to form a valid calibration. And in essence, we no longer have that with dust. The reality and the real world, I'll provide an example of really how particular monitors' responses of low-level clusters impact continuous emission monitor and standard reference method calibrations. So ultimately on this graph, the SEM calibration lines can change massively depend on a large number of factors. Any lift in emissions would typically cause divergence between the SEM and SRM correlation. And I'll cover this further in the second half of the presentation. So again, to take out a few more extracts from the Environment Agency Technical Guidance Note M20, and also from the 14181 and 13284 Part 2 standards. In this instance, EA Technical Guidance Note M20 3.5.15. If the emissions are typically below the 95% in confidence interval of the emission limit value, then an AST is permitted instead of a Qual 2. So to put this into context, for sites with an ELV of 10 milligrams, this caveat would only apply with emissions below 3 milligrams. So just taking this set in stone, ultimately anyone from an emission limit value of 10, you have to perform or attempt calibrations, Qual 2 calibrations, unless your emissions are continually below 3 milligrams per meter cubed.
Hi, Paul. I've been told your presentation is no longer streaming. Can we just check?
Okay.
There's a message in the chat.
Right, let me just share that again then.
Well, I would hold off 1 second.
Okay.
Can we have some support on that? Can anybody confirm whether it's streaming or not? Oh, all good now.
Go to your next slide, Paul.
Next slide.
All good.
Okay. So am I okay to carry on?
Just try one more.
Yeah.
Hang on a second, let me come out. What I'm going to do, I'm going to share the screen again. Does that look better?
I think people are saying it's back. It's back now, so no problem.
Okay. Do you want me to step back or do you want me to continue from here?
I would continue. I think it's just one or two people.
Okay. So just moving on, yes, just to confirm, there is a caveat within Environment Agency Technical Guidance Note M20 that if your emissions are typically below 95% confidence intervals at the ELV, then the AST is permitted instead of a Qual 2. So really, just to expand on the Environment Agency Technical Guidance Note M20 section 3.5.2 monitoring strategy states for low emissions, reduced measurements with longer sampling times may be satisfactory. For example, the AST may consist of 5 measurements each with a sample duration of 1.5 hours, thus providing a total sampling period of 7.5 hours. This approach helps to reduce the standard deviation by minimizing uncertainties in the SRM. And really this, in context, go back to the validation work. This is the same point that if you extend the sampling time, the original validation work was based around 30 minutes. So if you extend the sampling time, but obviously this doesn't go on forever, that there is limits in how long you can extend the sampling time. But ultimately, if you sample for 1.5 hours, it does provide reduced uncertainty and hopefully variability. An extract from Environment Agency Technical Guidance Note M20 3.515 calibration procedure C for low-level clusters. The statement reads that standard reference method measurements are used to verify that the continuous emission monitor respond to even low concentrations of the determinant. The difference between the average of the standard reference method and continuous emission monitor results should not differ by more than half the allowable 95% confidence interval of the daily average ELV. For particulate, if an ELV of 10 was applied, this implies that the difference between the SEM and SRM, continuous emission monitor and standard reference method, should be no more than 1.5 milligrams, which is unlikely given the uncertainties involved at this low level. Think of this in the context of the BSEN 3284 Part 1 validation tests, where results varied between 6 and 19 on plant A and 0.3 and 6.8 on plant B. Furthermore, EA Technical Guidance Note M20 in section 3.5.16, Qual 2 for particulate SEMS, it does recognise that error associated with the SRM standard reference method increases significantly when the dust concentration below 5 milligrams. Great caution should be applied when making a Qual 2 assessment on processes with dust levels lower than 5 milligrams. Straight away, go back to an earlier slide where you had a context if you were below the 95% confidence interval, which is 30% for particulate matter for dust. So for a 10 milligram ELV, the threshold for conducting Qual 2 assessments is really above 3 milligrams. But there's another statement in the technical guidance, which says that really errors associated with the standard reference method, especially around particulate matter, increases significantly below 5 milligrams, and really this should be taken into consideration. Calibration ranges. So in BSEN 14181, section 6.5, the valid calibration range is either the calibration range from 0 to the maximum value of the calibrated continuous emission monitor, measured values at standard conditions, determined during the Qual 2 procedure, quality assurance level 2, plus an extension of 10% or to 20% of the emission limit value, whichever is greater. BSEN 13284 Part 2, which is derived from 1481, provides guidance specific to dust measurements. In section 8.2.6, the valid calibration range, it gives an allowance for the difficulties with low dust calibrations. And so for dust, the calibration range may be extended to 50% of the daily emission limit value, provided the existence of a linear calibration function is proved and the obtained coefficient of determination R squared is at least 0.8. So again, to cover this point a bit further, and just to put it into context, BSEN 1481 section 6.5 covering valid calibration ranges. If a qual2 calibration was value achieved plus 10% will become the valid calibration threshold. If the highest SEM value during the calibration was 6 milligrams, this would set the valid calibration range from 0 to 6.6. And with calibration in place, new qual2 will be required if more than 5% of the number of continuous emission monitor measured values calculated weekly were above the 6.6 milligram threshold for more than 5 weeks. So with these sort of caveats in place, without question, with emission limit values of 10 milligrams or less, and the difficulty in achieving an acceptable valid calibration range will lead to an increased number of qual2 retests and will result in significant additional operator costs for no additional environmental benefit. BSEN 13284 Part 2 Annex D, it does give allowance for trying to extend the calibration range by changing the dust concentration. The information in Annex D provides 3 methods for extending the calibration range. 1, by changing the plant load. 2, by changing the operation of dust arrestment plant. 3, injection of dust. It should be recognised that in many cases, it's not possible to increase the dust level in a representative way. And quite often, and we've tried this in the past, the higher points will often sit as outliers in the assessment and cannot be used. So the standard does give allowance for methods to try and achieve a valid calibration range, but in reality, it is still very difficult to achieve, and you often end up with just a low-level cluster. BSEN 14181 6.7 test availability and test calibration, which is in section G.2.4. Both of these calculations use a standard deviation, which is derived from requirements legislation. So the standard deviation formula is used in both the outcome of tester variability and the tester calibration calculations. Without question, lower ELVs, which forms a big part of the standard deviation calculation, will lead to a greater number of failures on this part of the qual2 and AST exercises. If people want to do the simple maths, when earlier ELVs were in place, there wasn't so much of an issue on failing these parts of the standard, but as emission limit values have got lower, it's become harder and harder to pass this requirement of the standard without question. So as best available technique, associated emission levels reduce, and in turn emission limit values reduce, we will see more failures of this part of the standard. And there doesn't seem to be any sort of caveat in the standard for overcoming this difficulty. So what happens if we can't drive a valid calibration due to very low particulate levels? EA Technical Guidance Note M20 does have a clause, 3.5.4. So regulation when particulate monitor cannot be calibrated. And it states, if a test report states that a particulate monitor cannot be calibrated due to very low emissions, then the output of the SEM will be qualitative. Whilst it may be possible to intuitively set the reading of the SEM to provide an output in milligrams per meter cubed, a concentration, such regions will be an approximation at best, with a strong likelihood of high uncertainty levels, unless it's possible to produce a higher representative emission from the process. In this case, it's recommended that such regions should be disregarded for regulatory purposes, including pollution inventory reporting. So just to summarise on some of the technical issues with the standard reference method and technical guidance notes, it's generally agreed for particulate matter that sub 5 milligram calibration should not be attempted. Attempts to calibrate between 5 and 10 milligrams will lead to an increased number of repeat qual2 tests due to either failures of the test of variability, test of calibration, or from invalid calibration ranges. If a test report states that a particulate monitor cannot be calibrated due to very low emissions, then the output of SEM will be qualitative and really should be disregarded for a regulatory purpose, including pollution inventory reporting. Continuous emission monitors should be used for qualitative monitoring of emissions only. So again, before we move on to the continuous emission monitors and the impacts that on those, I just want to repeat again before we continue, to measure the dust concentration from continuous emission monitors, the correlation between the primary measured variable scattered light intensity and the actual dust concentration in the duct must be established. For this purpose, the dust concentration must be determined by means of gravimetric measurement. Again, it's just confirming the point that no continuous emission monitor for particulate When it comes out of the box, we'll give you a concentration in dust straight away. It has to be aligned to a series of standard reference method tests. And the above statement is taken from the operating manual from an MCERT approved SEM and holds true for all certified approved particulate analyzers currently on the UK market, again, regardless of manufacturer or measurement principle. So one major difference between the standard reference method and continuous emission monitors is influences on the continuous emission monitors from particular characteristics. So in order of prevalence, particle size, particle color, particle shape, opaqueness, moisture or changes in moisture, reflectivity, all of these can have an impact on the response from a particular continuous emission monitor. But none of the above characteristics affect the standard reference method result, but they really can have a significant impact on SEM responses. So I'll go into these in more detail. Just out of interest, the top order particulate size from a cement manufacturing point of view, the particle size in the cement process can vary between 0.5 microns to 100 microns. So there is a great deal of variability within the cement process. Other processes vary to a different degree. Some processes will have a uniform and spherical dust particle, but this will vary from process. So just expanding on particle size, think of particle size as rain and fog. Just an analogy from everyone typically drives a car. So without question, the response from the continuous emission monitor will change significantly when variations in particle size are experienced. Again, just to confirm, standard reference method values are unaffected by variations in particle size. Again, this effect can lead to deviation between sort of standard reference method and continuous emission monitor responses. So think of your eyes at night as a detector of the continuous emission monitor, and think how the rain and fog changes what you see. This is a good example of how continuous emission monitor responses change due to particle size. I've got a couple of examples of a loss in light optical monitor and a laser scatter monitor, and really think of how their detectors will change the response level compared to particle size when you think of rain and fog. Another example of this is taken from filters taken from the cement process. So they're observed under a microscope. So the results were seen on these two filters were for the same time from the same stack, but you can see that filter 1 has a far more uniform spread of particulate matter, and filter 2 has larger size particulate matter, and it's more ununiform. Ultimately, the concentrations on both of these filters was the same after the filter had been weighed, but in question, the continuous emission monitor response would change significantly between filter 1 and filter 2 due to the changes and variations in particle size. Again, just to confirm, standard reference method test for particulate matter 13284 part 1 is unaffected by variations in particle size. Dew point, every gas mixture contains a defined quantity of humidity. The maximum possible saturation humidity is dependent on the temperature. If air is continuously cooled with constant absolute air humidity, the relative air humidity increases up to 100%. If the air is further cooled, the humidity condenses as water droplets. Dust monitors cannot distinguish between water droplets and dust particulates and can see the two as the same. Any water droplets present will affect the continuous emission monitor response, especially variable levels of water droplets. Water droplets will not affect the standard reference method result as the filter is dried before weighing. So to summarize the influence on particular continuous emission monitor characteristics, the SEM response and valid calibrations are dependent on the particle characteristics remaining the same, consistent. Any change in particle size, color, shape, opaqueness, reflectivity, or stack moisture levels combined with low temperatures can significantly change SEM responses. Any small change in particulate characteristics following quality calibrations will change continuous emission monitor responses, potentially invalidating existing calibration curves, especially with emission limit values of 10 milligrams or less. The above would be an increased number of qual 2 retests and will result in significant additional operating costs for no additional environmental benefit. So what happens, again, when particulate monitors cannot be calibrated, there is a suitable alternative. And this is covered in Technical Guidance Note M20, section 3.5.4, which states the output from the particulate monitor can demonstrate whether the process is under control or not. Such output should be regarded as an indicative trend that can demonstrate if there's a significant change in the process. So think of the control chart approach as qual-free for particulate matter, to show that the abatement and the process is under control and the site are remaining compliant. So just to expand on section 3.5.4, if the output from the SEM changes and rises above the upper margin of error, then the operator takes immediate action to investigate the cause of the change. If the output of the SEM and then takes appropriate action to ensure that the readings return to within the margins of tolerance as quickly as practicable. In simple terms, and from a continuous emission monitor perspective, an increase in response and a noisier response is indicative of a deteriorating abatement plant. With the old adage that abatement plant typically don't fix themselves, if the signal continues to increase and gets noisier, that is indicative of abatement plant deterioration. And on the trend below, you can see where the control chart has picked up that lift, has picked up that increase in noise, and the plant have basically taken steps to bring the abatement plant back under control. So you can see at the end of the control chart that everything reverts back to control line level. So again, Technical Guidance Note M20 3.5.4, when a particulate monitor cannot be calibrated, the control line, which we see as green, the warning, which is amber, an action line, which is red on the chart below. The required thresholds can ideally be set and reviewed after each routine monitoring standard reference method assessment. The action required upper margin of tolerance is always set below the ELV to ensure that compliance to ELVs is always maintained. So you've never set the upper threshold, the action required threshold, close to the ELV, because obviously just remember back to the influences on continuous emission monitors. As the levels increase, the uncertainty increase, and obviously the correlation with the standard reference method tends to deviate as well. So it's important to always set the thresholds well within compliance to ensure that compliance with emission limit values is maintained. Care has to be taken on some processes if this control chart methodology is used, especially with processes that have greater variability in particle size and moisture levels due to product changes, which will affect the SEM response. These responses can be recognized by step changes up and down, not just increasing and getting noisier in SEM responses, rather than an increase in progressive noisier signal, which is indicative of a deteriorating filter. So again, it must be recognized that the influence that particle characteristics can have on the continuous emission monitor, that if you see this on control chart as a step up and a step down, it's not a sign that action is needed. It's just really indication that the particulate characteristics are changing within this process. And really what you're looking for, again, to take action is an ever increasing and noisier signal. So Technical Guidance Note M20 from the Environment Agency, section 3.5.4, again, covering the section on regulation when particulate monitors can be calibrated. They offer two options on approaches to apply when reporting emissions for annual emission inventories. So the two approaches that operators could apply is A, using an average based on the results of the standard reference method periodic monitoring, or B, reporting a result which states the emissions are not more than a result based on the allowable uncertainty of the daily average emission limit value or similar medium-term average ELV expressed as a 90% confidence interval. So really, just to sum up at the end, what we have here, and really just taking a bit of the points and going into further detail from Rod and David's presentations, the uncertainty of the particulate standard reference method combined with the uncertainty and variability of continuous emission monitor responses, added together with lower emission limit values, is a perfect storm that presents a significant challenge to process operators in respect to BSEN 14181 and 13284 Part 2 compliance. And again, just to recap, Technical Guidance Note M20 from the Environment Agency, section 3.5.4, regulation when particulate monitors cannot be calibrated, offers a viable and alternative approach until new particulate SEM technologies, improve limits of detection, and reduce uncertainty thresholds can be found. Thank you for everyone's time, and if anyone has any questions, please feel free to ask away.
Thank you very much, Paul. I can't see any questions yet on the tab or in the chat. I think we've time for one or two just about.
Apologies for any visual difficulties seeing the presentation, or if there was any audio difficulties as well.
I think that was affecting one or two people specifically. I think people had to log back in. I can't see any questions. I'm just wondering, Paul, given the sensitivity to particle properties of optical devices, there's probably a case, you know, if you don't have very consistent particulate, a sort of beta attenuation gauge or something like that, which makes a more direct measurement of milligram per meter cubed, would be suitable. I'm guessing from what you said, there's nothing like that certified at the moment.
Not certified. So really, this sort of covers the limits of the current continuous emission monitors on the market. Without question, some devices are less susceptible to, shall we say, interference or effect from some characteristics. I know personally from experience that electrodynamic devices seem to show less impact from when you have a low temperature and varying moisture levels in a stack. So we know that sometimes optical devices and laser scatter devices can be affected significantly when you have low temperatures and water vapor droplets, but electrodynamic don't have as much impact from that actual characteristics itself.
Yeah, thank you. I think in our case, where we're mostly monitoring particulate downstream of wet abatement systems, those systems usually condition the particulate very well, both in terms of particle size, and we tend to get pretty consistent properties, to be honest. They're mostly spherical particles, but in your situation, I think you've got much more variability.
Yes, without question. Yeah, I think. Yeah, sorry.
So, Karen, which gives you a problem, I was just going to say. Yeah.
Yeah, and ultimately, yeah, without question, the issues on the continuous emission monitor responses will vary from process to process. And yes, so if you have a more uniform spherical dust, it's not so much of an issue. If you haven't had that, if you haven't got that much more variation, you still have an issue. That the issue will still be faced with low-level clusters and trying to generate a valid calibration line.
Yeah, indeed. Yeah. Yeah, we just need more sensitive reference methods, don't we?
Yes.
Well,
and personally, I think it would be really valuable to revisit the validation of the 13284 Part 1 standard, just to see where we are with that variability and uncertainty in the present day with extended test times, and because without question, improvements have been made in testing the standard reference method to low dust, but we really haven't got a feel for what sort of uncertainty and variability we have at this present day.
Yeah, we always felt you should be able to get down to maintain about 10% uncertainty down to about 3 milligram per meter cubed.
Yes.
You know, with suitable care, but it's not really the answer. I think probably new reference methods are needed, perhaps based on air quality approaches. You know, because they're already looking at very low concentrations. But that will be some time coming. And I've always wondered who actually gets that off the ground in terms of looking at a completely new approach.
Yes. Yeah, no.
From a standards point of view, yeah.
It does offer challenges, not only to manufacturers, but operators and regulators equally.
Yeah. Well, thank you very much. I'll just check the tabs again. Can't see anything. So thank you very much, Paul. I think it's appropriate for us just to take a half-an-hour break now. We'll be back on the original schedule, sort of. If we restart at 12:30 UK time in half an hour, 13:30 CET, with the second part of the program. So, thank you, everybody, and see you soon.